So it says water displacement is used to capture 25.0 milliliters of butane gas. In the classroom, the temperature is 27 degrees C and the pressure is 0.94 atmospheres. So I see several different variables in there. I see a volume, I see a temperature, I see a pressure, and it's asking me for moles. So pretty much if we see gas laws and it's asking me for moles, it's going to be PV, PV equals NRT. So I'm going to write out the equation. I'm going to list the variables. P, V, N, R, and T. Always write out your equation. Always list your variables. So the pressure in this, all I need to do then is look up the pressure. So it says 0.94 atmospheres. And I'm good with that unit. Volume, 25 milliliters. This has to be in liters, and we'll see why in a second. So remember, there are 1,000 milliliters in 1 liter, right? Milli. And so I go 1, 2, 3. So just remember that I'm going to move the decimal place 3 places to go from milliliters to liters. So the volume then would be 0.0250 liters. N in this case is moles. It's what we're looking for. So N just refers to the number of moles in the sample. It's a count. N is always in statistics and math. N is the number of something. The count of something, since we're not actually counting the atoms by themselves, we're saying N represents the amount of atoms. R then is 0.0821 liters times atmospheres on the top, moles times Kelvin on the bottom. And I'll show you why the crazy units look like that in a minute as well. So we can see then why we have to use liters. If R is in liters times atmospheres, moles times Kelvin, then all my units have to match. I can't mix and match milliliters and liters, so that has to match. So what temperature? Well, I can't use degrees Celsius ever anyway in gas laws, so I need to make sure that everything's in Kelvin. So remember, 273 plus the Celsius gives us the Kelvin. So that's an even 300 when I do that. So do your conversions right inside your givens over here. So, and that's 300K. So we're looking for moles. It's just algebra. I need to rearrange, right? So if it's on the top on one side, the R and the T get moved to the other side. So N is equal to PV divided by RT. So now I can plug things in. The pressure was 0.94 atmospheres times my volume, which is 0.0250 liters, divided by my R value, which is 0.0821 liters times atmospheres, divided by moles times Kelvin, 300K. And so now we can really see why we have to have that universal gas constant, that R value in there. Because if I didn't have the R value in there, nothing would cancel out. Atmospheres doesn't cancel out Kelvin, liters doesn't cancel out Kelvin, but here I can do liters cancels out liters, atmospheres cancels out atmospheres, Kelvin, Kelvin. I'm left with moles on the bottom, but moles is on the bottom in the denominator, so it actually means that we're left with moles on top. So now I just type into my calculator 0.94 times 0.0250 divided by 0.0821. And notice the 300 is on the bottom. So I could put the bottom in parentheses, but it's easier just to divide since it's on the bottom already. So divided by 300. And I came up with a very, very tiny number. So I came up with 0.00095421. So where do I round that to? I'm just going to go back to my givens then. So I'm going to go back to the givens in the problem. I have 3 significant figures there, 2 significant figures there, and 2 significant figures there. So I need 2 significant figures in my answer. So that would be 0.0095, and that would be moles.